Hello, in this video we are going to be looking at the parallel plate capacitor in an extensive amount of detail, and then going through an equally extensive example problem looking at all the different things that we can calculate with a in a parallel plate capacitor. Now before we get started, I want to kind of contextualize what we're doing here, and I'm going to do that using this diagram that I like, relating these four main concepts that we've developed in the electrostatics unit: the electric force, the electric field, electric potential energy, and voltage. All right, so right now what we've said, or we've been doing a lot of, is looking at these four concepts in the context of point charges. So we looked at Coulomb's law for the electric force, and then a similar equation for the electric field. And one of the things that we noted was that to get from the electric field to the force, we just had to multiply by this Q2, this charge that was in the electric field. And then reciprocally, if I wanted to get from the force to the electric field, I would just divide by Q. All right, and then we turned over to looking at energy and voltage and wrote down these equations, where again, we saw that to get from a voltage to an electric potential energy, I had to multiply by Q and then the reverse to divide. Now, part of what we want to do today is sort of complete this box and be looking at the connections between the electric field and the voltage. We've kind of seen the relationship between the force and the electric potential energy. One of the ways that we can relate those is using this concept of work, where we're saying that the work that's being done on a charge is equal to the electric potential energy, and so we can say that that's just this force times the distance. But one of the things that's happening here is that the force has to be constant in this definition of work. Right? So the force has to be constant in order for that to be true. Right? So one way that I could write this down is that if I've got a constant force, then I'm just multiplying or dividing by the distance that this charge is moving to get that change in energy. Sorry, that's a change in energy. As long as that force is constant. Now, when I'm looking at this situation, all right, the Coulomb's law that I've written down for point charges, as I'm moving a charge, that force is not going to be constant. So this definition wouldn't work, which is why the calc-based definition is going to be integrals and derivatives to get from one to the other. So specifically that if I want to go from the electric potential energy to the force, I'm taking a derivative with respect to the distance, and then integral going the other way for those of you who are in calc. If we want this force to be constant, in this situation what that means is that the electric field has to be constant. And so what we want to do is be looking at a situation where the electric field is constant. And what situation is that going to be true in? Well, that's going to be true in a parallel plate capacitor. And so what we're going to be able to see is that, again, off to the side here, that the change in the voltage across a parallel plate capacitor is going to be equal to the electric field times some distance, right? Similar to what we're seeing with the change in the potential energy. But again, this electric field has to be constant. So we're really introducing this idea of a parallel plate capacitor so that we can be looking at the relationship between the electric field and the voltage without having to do any sort of calculus. All right, so what is a parallel plate capacitor? Well, first of all, a capacitor is an element that you might find in a circuit. So circuitry is the sort of thing that you would find in your walls, right? Electricity. You can light up light bulbs. You can do things with audio, right? The ability for the translation between the electricity in your audio system in your car and sound, right? That's going to be a circuit. I could go on. All right, there's just a million different ways in which we use electricity in modern society, and one of the ways that we can manipulate electricity to do what we want is using this thing called a capacitor. Now, what it's going to do is it's going to store energy. That's going to be one of its main functions. And it's going to store energy by storing charges. And specifically, it's going to store charges on some sort of conductor, right, which is usually a metal. And in this case, the parallel plate capacitor, we're looking at a couple of metal plates which are parallel to one another. All right, so if I'm drawing a diagram of this, I can just do an edge-on view, right, and draw a couple of, draw a couple of parallel lines, horizontal parallel lines. Wow, okay, so these just are not gonna, it's just not gonna happen. Okay, so those are gonna be, we're gonna say those parallel, okay? And so I can get a bunch of charge on these plates. That charge is stored there, and then if I need it, I can suddenly unload that charge into my circuit and get a little extra bump in energy. Okay, so I'm going to walk us through how these plates end up getting charged in a circuit, mostly just because one of the things that we're going to find is that one of the plates is positively charged. So let's look at how we are going to charge this parallel plate capacitor. All right, so first of all, we're going to hook this up to some sort of source of charges. One of the simplest ones is going to be a battery. All right, so I'm going to have some sort of battery that I've got, and I'm going to hook up this battery to each of the plates of my capacitor. All right, and this battery is going to send negative charges, electrons, down the wire, and they're going to end up on one of these plates. All right, so I'm going to have a negative charge on this plate, and that negative charge is going to be creating an electric field. And that electric field is going to consequently push a negative charge off of the other plate, leaving a positive charge exposed. All right, so if I have one negative charge, one electron on the plate, and I get one proton exposed on the other. All right, and then this just keeps happening. All right, another electron shows up on the bottom plate, pushes off an electron, and I get a positive charge on the top plate, and so on and so forth, until eventually this plate becomes fully charged, right? It just cannot hold any more charge on it. All right, and if I check, okay, so I've got 8 negative charges on the bottom and 8 on the top. It's going to be significantly more than that. It's going to be like in the billions of charges that we have on these two plates. But anyways, the point is that, right, whatever positive Q I've got on the top, I'm going to have a negative Q on the bottom. All right, and so that it's going to be equal and opposite charges on these two plates. The other thing that we can do in this situation is start thinking about the electric field. Right, so I've kind of already spoilered the idea that this is going to be a situation where we've got a constant electric field. Right, that's the thing that we need in order to be looking at this relationship between the electric field and the voltage. But right now, I just want to be thinking about the direction. And what we've said before is that positive charges have electric fields that point away from them. Negative charges have electric fields that point towards them, and so I'm going to have an electric field that's pointing away from the positive charge and towards the negative charge, and so it's going to set up this electric field that's just pointing from one plate, from the positive plate to the negative plate, all right, where this electric field is perpendicular to the plate. All right, we could go through some sort of proof showing why it's perpendicular, but the gist of it would be that if I start looking at multiple charges, I would see that the x components in this case would end up canceling out because of this long line of charges that I've got. So at least in between the two plates, right, I would just have this y component, so it's perpendicular. Okay. So let's look at the magnitude of this electric field. And this is one that I'm just going to kind of have to write down. There is a proof for where this comes from, kind of from first principles, but it deals with something that's called Gauss's law that we haven't looked at in this course. But it does exist, but once again, we're in a situation where I'm just going to have to kind of wave my hands and say, this is what it is, and you're going to have to accept it. So sorry about that, but here we go. Okay, so the electric field for a capacitor, parallel plate capacitor, is equal to the magnitude of Q, the charge on one of the plates, divided by the area of one of the plates, and this constant epsilon naught. All right, epsilon naught being the value of 8.85 times 10 to the negative 12. All right, and then as we saw, if we just take that electric field and multiply it by a charge that we're placing between these two plates, I would be able to get the force on that charge. All right, and then now that we've got this electric field that is constant, right, and I'm saying that's constant because it's depending on the charge on the plates, it's depending on the area of the plates, but it's not depending on the distance, right? There's no r or x or y variability to it. So if I move a charge from, say, one plate to another, so if I introduce a second positive charge in between here, and I move it from the positive plate to the negative plate, or I guess it would move, right, from that force, the distance that it's moving is not going to change the electric field. All right, so the distance that we are from these plates doesn't change the magnitude of that field, and so we've got that requirement that the electric field is constant, and so now the voltage between these two plates, the change in the voltage, is going to be equal to the electric field times the distance that we're moving that charge. So whatever the voltage between these two plates are, is going to be found by multiplying it by the spacing between these two plates, so this distance d. Right, one of the things that this is saying is that the electric field is going to be, the voltage is going to be increasing linearly. All right, so if I have, I'm just going to draw this diagram again to kind of clean it up. All right, if I've got two plates, this is my negative Q on the bottom, positive Q on the top. All right, I can have some sort of change in voltage, but one of the things that can be really convenient is to make it so that the negative plate is always at 0 volts. All right, where the location of the 0 volt voltage is in space is something that we get to decide. We can call voltage arbitrary up to a constant. And so one of the things I can do is say, okay, the negative plate is going to be at 0 volts, and so then the positive plate is going to be at some sort of positive voltage that we can calculate using this equation. And then if I also put my origin at this point, so my 0 for the y in this case, at that negative plate, I can create a graph that's saying, all right, my voltage as a function of this y distance is going to start at 0 at y equals 0, and then it's going to linearly increase until we get to this final voltage V at my distance d, the spacing between my plates. All right, where the slope of this graph is going to be the electric field. All right, so more generally, I can say that the voltage as a function of this y distance or x distance, depending on how they're oriented, is going to be equal to the electric field times that y distance, where I could also say that this electric field is the change in the voltage between the two plates of the capacitor. All right, so I could say that this is VC divided by that spacing, D. Right, going back to this relationship, the electric field would be the change in voltage divided by that spacing, and then multiplying it by Y, that distance that I am from the negative plate. All right. And then last, this probably is the most important concept in this lesson, which is that we're saying the voltage is increasing from 0 to some sort of positive voltage, and the electric field is going to be pointing from the positive plate to the negative plate. And so what this is showing is this general truth, which is that the electric field points in the direction of decreasing voltage. All right, so the electric field is pointing down and the voltage is decreasing from this positive value to 0. We can also see that this is more generally true if we go back to looking at the point charges. So if I have a positive point charge, I've got the electric field which is pointing away from that positive charge, and the magnitude of my voltage is going to be decreasing as I'm getting farther and farther away, something that we can show with my equipotential lines getting farther and farther apart. For the negative charge, the electric field is pointing towards the negative charge, and while the magnitude of my electric field, the magnitude of my voltage is getting bigger as I'm getting closer to that negative charge, since it's a negative charge, that voltage is going to be negative. All right, so it's decreasing to the left on my number line, right, getting more and more negative. Okay, so the electric field is going to be pointing right in the negative direction. It's going to be pointing in the direction as the voltage is getting more and more negative. And we could see that in the parallel plate example as well, right? If instead of this being 0 volts, I had this be negative 150 volts, right? And I was still increasing up to some voltage for my capacitor, but now 150 volts less, right? I'd be still pointing towards the direction of this getting more and more negative. Okay, so I think that's it for the basics of what we need to know for this particular unit. I'm just going to go back and say, okay, the electric field capacitor, this one's a pretty important equation. Change in voltage across this capacitor is a pretty important equation that we're going to need to know moving forward. Right. Okay, so a parallel plate capacitor has circular plates of radius 2 centimeters with a spacing of 4 millimeters, and 4.3 times 10 to the 9, 4.3 billion electrons are transferred from one plate to the other. Right, so if the potential difference between the plates is 400 volts, we're going to find a bunch of stuff. Okay, so let's just start by setting up a diagram. All right, so here are my two circular plates. I've got the radius of 2 centimeters, spacing D of 4 millimeters, and a potential difference of 400 volts. Right, it's also telling us that this 4.3 billion electrons are being transferred. So if I'm transferring electrons from one to the other, this is a way, a kind of shortcut to say, all right, I've got the same charge from one plate as I do on the other, which is what would happen anyways as long as I'm charging that parallel plate capacitor. But this is going to be what gives us the charge on each of these plates. All right, so for right now, I'm going to say N, the number of electrons, is this 4.3 billion. And then to find the charge on both of these plates, either of these plates, I'm going to just take that number of electrons and multiply it by the charge on each electron, which is that fundamental charge E, 1.6 times 10 to the negative 19th. And I can calculate what the charge is on these two plates. So for right now, I'll just say the left plate is positive, the right plate is negative, and we can go on from there. All right, first part, A, is asking for the electric field between the plates. All right, so we're looking at a parallel plate capacitor, so we're going to use this capacitor equation that we wrote down before. we have our epsilon not constant. The area is going to be the area of one of these plates, and so since they're circular, I'm going to be looking at the area of a circle, pi r squared. And then Q is what we just calculated before, so substituting this all in, I've got a final equation for the electric field between my two capacitors, and then based on the way that I've drawn this, I would have my electric field pointing from positive plate to negative plate, again perpendicular to those plates, so this would be in the, I suppose, positive x direction, or we can just say to the right for the direction. Okay. Part B is looking at the force on an electron 1 millimeter from the negative plate. Okay. Again, the electric field does not depend on the distance from the plates that you are, right? There is no x or y or d term in this electric field equation. And so the force would be the same on an electron no matter where you were between these two plates. So I could have said 1 millimeter, 2, 3, 7, nope, 4.2, nope, 3.2, right, whatever I want, and I would still get the same answer, okay? And to get that answer, right, we're saying that the force is equal to the charge times the electric field, all right? And so the charge in this case is of an electron, and so it would be that negative E, negative fundamental constant, and so I can get, again, that final equation. So the force would be the negative E times the electric field of the capacitor that I found before. All right, that negative sign is actually telling me that's going to reverse direction. So if I imagine putting a negative charge somewhere in here, right, it's going to go towards the positive plate, away from the negative plate, so the direction on that is going to be to the left or in the negative x direction. Either way is going to give us that answer. Okay, part C, I'm looking for the potential between, or the potential 1 millimeter from the negative plate. Okay, so we talked about this a little bit already, but let's draw this graph again so that now that we've got a little bit more context to see what we're talking about. All right, in this case, we're looking at how it's going to change in the x direction, just based on how I've oriented my plates and the voltage. I'm going to put my, I really should have put these the other direction, okay, 0 volts. I guess I can just switch this because I've been saying to the left and to the right. Okay, I'm going to put my origin over here. And so as I increase from 0 to my 4 millimeters, I'm going to be increasing my voltage from 0 to 400 volts. All right, and that's going to give me some point, and it's a linear increase, where the slope of this graph is the electric field, and so I'm looking at this at some point, or at the point of 1 millimeter. All right, so what is the what is the voltage at 1 millimeter? Now, I could do the calculation. I could say, all right, the voltage is equal to the electric field times this x direction. All right, so if I've got the electric field from part A, I just multiply it by 1 millimeter, and that would give me my voltage. The other thing that I can see is that as I'm going from, right, 1, 2, 3, 4 millimeters, right, I've got up to 400 volts. And if this is linear, then this is also going to be linear on this axis. And so I would have it going from 100 to 200 to 300 volts. All right, so if we did this calculation out, what I would expect my answer to be for part C is 100 volts. Okay, and finally, part D, what is the electric potential energy of an electron at that point? Well, the relationship between the voltage and the electric potential energy is that the electric potential energy is equal to Q times the voltage, and we have to be looking at the voltage at the particular point, right? So if we want the electric potential energy at 1 centimeter from the negative plate, I have to be looking at the potential or the voltage 1 centimeter from the negative plate. Fortunately, we've already calculated it, right, in this last part. And so I can just say, all right, the electric potential energy is equal to that negative E, right, the charge on an electron, times this voltage, I said voltage 1 for 1 millimeter, that we calculated in part C. Okay, I think that's it. All right, next week we're going to be starting to talk about circuits in more detail, and until then, good luck out there.